Hello guys, welcome back to the channel. My name is Nidhi and I am a student currently studying at Sri Venkateswara College of Engineering, Bangalore, pursuing my BE in Computer Science and Engineering. In this presentation, we will explore the concepts of Boolean algebra from the course of Digital Design and Computer Organization. We will see its basic operations and how these are applied in digital circuits and logical expressions. Boolean algebra is a branch of algebra that deals with logical operations on variables, where the values of variables are limited to two states. One is true and another is false. It is introduced by the English mathematician George Boole in the mid 19th century. Boolean algebra provides the mathematical foundation for logical reasoning and forms the core of modern digital circuit design. In contrast to elementary algebra, where the numbers represent quantities, Boolean algebra uses binary variables and logical operators like AND, OR, and NOT to represent truth values. These logical operations have been essential in the development of digital computers, where binary numbers and logical operations are physically implemented in circuits. Moving on to its fundamental, the main components of Boolean algebra are binary variables, truth table, and basic logical operators. Binary variables can only take two values. Truth table lists all the possible input combinations for Boolean algebra and shows the corresponding output for the operations. For n variables, a truth table will have 2 power n rows representing all combinations of zeros and ones. The basic logical operators are AND, OR, and NOT. Under AND, the output is true only if both the inputs are true. The symbol for AND is A dot B or A and B, where A and B are the binary variables. Here is the truth table of AND operator. Moving on to OR, the output is true if at least one of the input is true. The symbol for OR is A plus B or A or B. The NOT operator inverts the input value. If the input is true, the output will be false, and vice versa. The symbol of NOT operator is a tilde symbol followed by the binary variable, or it can be also written as not A. Boolean algebra follows specific laws and rules that simplify Boolean expressions and help design efficient digital circuits. The primary laws are listed here. First, commutative law. The order of the variable does not affect the result of an AND or OR operation. For AND, A dot B will result to B dot A, and for OR, A plus B is equal to B plus A. Second, associative law, where grouping of variables does not affect the result of AND or OR operations. For AND, A dot B dot C is equal to A dot B dot C, and for OR, A plus B plus C is equal to A plus B plus C. Third is distributive law, where AND distributes over OR and OR distributes over AND. For AND, A dot B plus C is equal to A dot B plus A dot C. For OR, A plus B dot C is equal to A plus B dot A plus C. Fourth is identity law, where AND with 1 or OR with 0 will preserve the original expression. For AND, A dot 1 will result to A, and for OR, A plus 0 will again result to A. Next is complement law, where a variable which is multiplied with its complement results in 0, and if it is odd with its complement, it results in 1. For AND, A dot A prime is equal to 0, and for OR, A plus A prime is equal to 1. Sixth, null law. AND with 0 always results in 0, and OR with 1 always results in 1. That is, for AND, A dot 0 is equal to 0, for OR, A plus 1 is equal to 1. Under idempotent law, AND or OR of a variable with itself result in the same variable. For AND, A dot A is equal to A, for OR, A plus A is equal to A. Eighth is involution law, which implies double negation of a variable results in the original variable, that is, prime of a prime is equal to a. What is a Boolean expression? It is a logical statement that results in a Boolean value, that is, a true or a false. Here in the example, you can see f is a function which is equal to a dot b plus c prime. This expression can also be written as a and b or not c. Boolean expressions are built using logical operators such as and, or, and not. As we know, a Boolean function is a function that maps input Boolean variables to an output Boolean value. A function can consist of multiple variables combined using logical operators. You can see this in the example. Moving on to simplification of Boolean expressions. Boolean algebra allows for the simplification of Boolean expression to minimize the number of operations and logic gates needed in digital circuits. Simplified expressions result in more efficient circuit designs. Here is an example of simplification where the expression f is equal to a dot b plus a dot b prime can be simplified using the below laws. So at first, after applying the distributive law, f will result into a dot b plus b prime. Then we know that under complement law, b plus b prime will result into 1. So f becomes a dot 1. And finally, by applying identity law, f results to a. So the simplified expression is f is equal to a. And in the very next step, you can see how our truth table is drawn. A truth table shows all the possible combination of input variables and the corresponding output of the Boolean function. Now let's see the principle of duality in Boolean algebra. Duality is a fundamental concept in Boolean algebra that states every algebraic expression remains valid if we swap the and or operators and interchange the constants 1 and 0. So we can find that every Boolean algebra expression has a dual. To find the dual of an expression, apply the following rules. Replace and with or and replace 1 with 0 or 0 with 1. For example, if the original expression is a plus b dot c, then the dual expression can be written as a dot b plus c. Applications of duality. Duality simplifies the process of deriving alternative circuit design, and it is particularly useful when minimizing logic gates or finding equivalent Boolean expressions. Duality is important because of its simplicity and consistency. It allows the transformation of a Boolean function into an equivalent form without changing its functionality. Also, dual expressions are logically consistent with the original and can be used interchangeably in many digital logic applications. In the slide, you can also find De Morgan's theorem, which are very crucial for transforming and simplifying Boolean expressions, especially when working with complements. De Morgan's first theorem states that the complement of a product is equal to the sum of the complements. That is, A dot B, the whole complement, is equal to A complement plus B complement. De Morgan's second theorem states that the complement of the sum is equal to the product of the complements. That is, A plus B, the whole complement, is equal to A complement dot B complement. Boolean algebra plays a critical role in various fields, particularly in digital electronics and computer science. Some of its most significant applications are listed here. Digital circuit design. Boolean algebra is the foundation for designing digital circuits. Logic gates are built using Boolean expressions. Complex digital systems like microprocessor and memory units are constructed using simplified Boolean expressions to minimize the number of gates required. Networking and communication systems. Boolean expressions are used to model the behavior of routing protocols, firewalls, and switching circuits. The design of packet filters, which determine how data packets are transmitted across a network, relies on Boolean logic. Computer architecture. Boolean functions are extensively used in computer architecture to implement arithmetic operations, decision making logic, and data processing. Operations like addition, subtraction, and multiplication in computers are carried out using binary logic. Boolean expressions are also used in the design of ALUs and control units of processors. Boolean algebra allows the simplification of complex logic circuits. By applying Boolean laws, unnecessary gate can be eliminated, which reduces the overall cost, power consumption, and the size of digital circuits. Error detection and correction. Boolean algebra is used in the design of error detecting and error correcting codes, such as parity bits and Hamming codes. These methods are employed in communication systems and computer storage to ensure data integrity. Artificial intelligence and machine learning. Boolean logic forms the basis of decision making algorithms in AI and machine learning systems. It is used to design binary classifiers that separate data into distinct categories. In conclusion, Boolean algebra forms the backbone of logical reasoning and digital circuit design. Its ability to represent and manipulate logical expressions using binary variables makes it indispensable in modern technology. Boolean algebra helps simplify complex logical systems, allowing for the creation of efficient, reliable digital circuits that power computers, smartphones, and countless other electronic devices. As we have already seen, Boolean algebra is widely applied in various fields, particularly in computer science, algorithm design, and electronics. So, mastering Boolean algebra provides the tool to simplify complex systems, making them more efficient and easier to understand. As technology continues to evolve, the principle of Boolean algebra will remain crucial in optimizing digital circuits, algorithms, and automated systems, ensuring that technological innovations are built on a solid and logical foundation. I would like to end the presentation here. Thank you so much for watching.